Exponential equations can be used to model situations where a quantity grows or decays by a given factor. In this case, what we're doing is we're multiplying. Okay, so we're going to end up multiplying a number. Okay, I'm going to give you kind of the short version of the notes, but here we go. Examples are the population in a city can grow by 10%, a car can lose 6% of its value each year, or a savings account can earn 3% interest each year. We're going to be talking both about percent decrease, where a number is getting smaller. Then we have what's called a decay rate, or a percent increase, where a number is getting bigger, and we have something called a growth rate. Here's an example of how to use this kind of formula to figure it out. Okay, so remember, I'm always starting with 100%, and then I'm either subtracting a percentage or adding a percentage, and then I'm changing it to a decimal by dividing by 100. Here's an example. The population of a city is growing at a rate of 5% per year. I'm always starting with 100%. Whatever the population of the city is, it's 100% of the population. Now, it's growing, so I'm going to add. I'm adding 5%. This becomes 105%. Okay, now I'm changing it into a decimal. You can change it into a decimal by just moving the decimal place 2 spaces to the right. Okay, that's how you do it. Or if you brain fart and you can't quite figure that out, or you feel like you have a mistake, you can take the percentage and you can divide it by 100. Look, I'm dividing by 100, 1.05. Look, that's what the notes say, divide by 100. Okay. The number of bacteria in a sample decreases by 10% every hour. So once again, I am starting with 100%, always starting with 100. In this case, I am decreasing, I'm subtracting 10%. Okay, that equals 90%. And again, I change this into a decimal. I'm taking the decimal place, moving it twice to the left, and that's 0.9. Okay, again, you could also put 90 divided by 100, it would get you the same answer. This is kind of a funny case, but this is starting with 100%. It says it doubles every hour. So what that means is whatever I have, whatever number I have, in this case we're talking about cancer cells, it's going to double. So the next hour, I'm going to have this, however much I had, plus this again. It's going to be, right, plus an extra 100%. That's the same as 200%. And when I change it to a decimal, it's the number 2. Okay, we're going to be looking at exponential functions. They always have the same format. Y equals A, the initial value, the starting value, times B, the growth or decay factor, that's what we just practiced calculating, to the power of X, okay? And the X and the Y, those are just gonna stay in the equation, they're just gonna stay X's and Y's, but you'll see when we get to an example. The X represents the independent variable. This is often time, in this case hour, in this case hour, in this case year. And the Y is the dependent variable. It just depends what the problem is about. So for example, here, the Y would represent the number of cancer cells. Here, the number of bacteria. Here, the population of the city, the number of people in the city. All right, let's take a look at an example. Your starting salary at a new company is $35,000 per year. Each year that you stay with the company and get a positive evaluation, you receive a 5% raise. Okay, the initial value is the starting value. It's this, 3,500. Sorry, 35,000. Now, the growth or decay rate. So remember, when I'm calculating growth or decay, it always starts with 100. Always, always, always. In this case, I'm receiving a 5% raise. This means my pay is growing. It's going up by 5%. So I'm going to write plus 5%. That equals 105%. And I'm going to change this to a decimal. So my growth rate is 1.05. Okay, now, in this next step, I'm writing the equation. I'm just copying here. This is Y equals, look, I'm going to write Y equals A, okay, A is 35,000, times B, 1.05, to the power of X. This is my equation. Now look, this X value is that independent variable. This is years, okay? And then this Y value is my salary in dollars. Now notice what's happening here. I'm going to take 35,000 and I'm going to multiply it by 1.05 once for every year. So here, for what will my salary be after 4 years of positive evaluations? Well, think about what's going to happen. This 35,000, every year I'm going to multiply it by 0.05 when I get my positive evaluation. Look, that's year 1. Then year 2, multiply it again. Year 3, multiply it again. But instead of multiplying over and over and over, what we do is we use the exponent. So I'm going to take this 35,000 and I'm going to multiply it by 1.05 4 times. Look, this means 35,000 times 1.05 times 1.05 times 1.05 times 1.05. So I'm going to put this in my calculator. So here's what that looks like in the calculator. 35,000 times, I'm just going to use the multiplication, times 1.05. Okay. Now look, to the power of this button right here. This one. To the power of, and in this case, what I want is after 4 years, to the power of 4. Okay. Enter. And here's what I get, $42,542. And now look, with dollars and cents, I'm gonna round to the number of cents. So that means I'm gonna cut off my number right here. Dollars and cents is 2 decimal places like this. So I'm gonna cut off that 8. Before I cut it off, I look, oh, that number is 5 or larger. So I'm gonna round this number up. So my total number ends up being $42,542.72. Okay, look. $4,542.70. Look, I rounded that last number up, 72 cents. Okay, anything with dollars, you're going to always round to 2 decimal places, right? That's dollars and cents. A lab sample contains 10,000 bacteria. After putting antibacterial spray in the sample, 12% of the bacteria die every hour. Okay, my initial value is, I'm starting with 10,000 bacteria. I'm identifying the growth or decay rate. So remember, I always start with 100%. Okay, and in this case, 12% are dying every hour. I'm subtracting 12%. I get 88%. And you can divide this by 100 or just move the decimal, but you get 0.88. Okay, and we know that this is a decay rate because it's less than 1, right? I'm subtracting from 100%. Okay, here's my equation. Y equals my initial value, 10,000, okay, times my decay factor, to the power of x. Okay, and in this case, we're talking about hours. My x is hours, and my y is number of bacteria. If I want to know how many bacteria are left after 5 hours, I'm going to put in my calculator 10,000 times 0.88 to the power of 5, right? X is hours. Look, I'm replacing the x with the 5. Now it says round to the nearest whole, right? A bacteria is a living thing, so you can't have part of a bacteria. You can either have 1 or 2 or 3 bacteria, but you can't have like 0.5 bacteria. Okay, so 10,000 times 0.88 to the power of, remember this button right here? That same button that's above your 6 on your keyboard, right? To the power of 5. Okay, I get 5,277 bacteria are left after 5 hours. Last example. This time I'm given the equation. Okay, so this, and it's the same format. And now remember, look, this is the initial value. So this models the amount of money I have in my savings account after X years. How much money did I start with? My initial value is $450. Okay, and is the amount of money increasing or decreasing each year? Well, let's take a look. This is my growth or decay factor. And watch what I'm going to do. I'm going to do what I've been doing in reverse. So look, it's a decimal. I'm going to change it back to a percent. I'm going to move the decimal place the other way. Now, how would I get 102.5%? We know I always start with 100%. Now look, this is more than 100, so I must have added what? 100 plus what is 102.5? Oh, plus 2.5%. So this is the change that's happening, right? I started with 100%. And the only way that I've gotten this decimal is by adding 2.5%. So I would say increasing by 2.5%.